Hello, can you still hear us?
I can hear you, yes.
Okay.
Yes, unfortunately, and unfortunately I cannot do anything about it. My windows are closed and everything, you know, I'm sorry for that. What kind of diagram are you talking about? Okay, let me see. Maybe I will just share. Maybe I will just share a window now. I mean the entire screen and see what happens. Okay. Can you see it?
Yes.
Okay. So this is a primary carbocation. Okay. So what seems to be a problem here? This is a primary carbocation here. So what seems to be a problem here, Granit? This is a line angle formula of the carbocation that has 3 carbons here. Oh, it's CH3 plus. There is nothing else to draw. So that would be like C, H, H, and H plus. But you don't do that, you know, just say CH3 plus, okay? So anyway, we are recording now. So here we have the methyl, primary, secondary, tertiary, allylic, benzylic. So for the carbocation to be allylic, it has to have a conjugated double bond. So double bond right next to the carbon with the positive charge. Okay, you can imagine. Well, from left, the lowest stability carbocation, the right benzylic, the highest stability. So you can also imagine that you have a allylic carbocation that is between 2 conjugated systems. So this is a secondary allylic. So because now the carbocation can be delocalized between 2 positions, so between this double bond here and the other one on the other side, that makes this carbocation more stable than the primary allylic. And again, if you have a tertiary allylic carbocation, it will be even more stable, because now you have 3 double bonds to delocalize this charge. So, and of course, that the same thing works for benzylic here. So if you have 2 phenyl rings attached to the methyl group here, it will be more stable. 3 will be even more stable. So this is basically what you do with the carbocations. Then you have a carboanions, and again you have a methyl carboanion, because it has a positive charge on it, and it has 1 hydrogen though. Then you have a primary, secondary, allylic, tertiary, allylic, benzylic. Okay. So in here, the primary carbocation, for example, would be a propyl carbocation. Okay. A secondary will be isopropyl carbocation. Tertiary will be third-butyl carboanion. Carboanion here. Allylic will have a double bond and lone pair of electrons here. So allylic carboanion, and the benzylic, of course, benzene with the methyl group and 2 electrons on it. Okay. So to distinguish the difference between carbocations and carboanions in the line angle formula, it's very easy. All you have to do is just look at the structure. If you see the structure that has 2 dots on it, that's carboanion, most likely for you, okay? If the same formula has a positive charge on it, that's a carbocation. Okay, so I'm going to erase that because I need some space. So now when it comes to the stability, the benzylic are more stable than allylic. These are more stable than methyl. And then you have a primary, secondary, and tertiary. So the stability is kind of reversed. Okay, so the benzylic and allylic carbocations are more stable because of the resonance stabilization, and the methyl primary, secondary, and tertiary, they are in the reversed order than the carbocations. Okay, so that's something you can kind of like have to remember a little bit. The last example that we'll have here will be the radicals. So radicals, they have 1 unpaired electron in the on the molecule somewhere, and you have a methyl radicals. Then you have a primary, secondary, tertiary, again allylic, benzylic. So the stability goes exactly the same way as for carbocations. So the methyl radical will be the least stable, primary, then secondary, allylic, benzylic. Okay, and the example of primary radical will be an ethyl, for example, radical. Secondary, isopropyl radical. Tertiary, third butyl radical. Okay, allylic, well, allylic radical, and benzylic, benzene ring with the methyl group and the radical on top of that. So you see, when you draw radicals, you don't put plus or minus, you just leave 1 dot for 1 unpaired electrons. And this is important for you to to understand, okay? Because I might ask you to draw the resonance structures of the radicals. So right now you know more or less about the stability of different kind of like carbocations, carboanions, and radicals. So with that, we can move on to the following questions here. Okay, so here we have some examples of carboanions. How do you know that? Well, because there's a negative charge next to the carbon here. Okay, so technically speaking, there are 2 dots here. When I ask you, oh, it's given here. It's the same as carbocations. See, I just put the notification for you, Deborah. Okay. So when I ask you questions about the to draw resonance structures of the carboanions, they will have a lone pair of electrons somewhere on the carbon, just to indicate that, well, this is what you need to move. Okay, and so let's start with the first example here. Double-headed arrow allow you to draw the next resonance structure, and you have a negative charge now on this carbon. So therefore, this is the most electronegative part of the molecule. So this is where you have to start drawing your resonance structures. So you will have to move these electrons towards the carbonyl carbon here, because that's the only place where you have the pi electrons or pi electrons available, and at the same time, the double bond will move towards the oxygen. And by doing that, you can draw now a new resonance structure that has a double bond here, single bond oxygen with 3 lone pair of electrons, negative charge on the oxygen. And there is also a double bond here. Can you draw more resonance structures for this molecule? Yes or no? Can you further delocalize this negative charge? No. So there are only 2 resonance structures for this carbo anion. And so let's talk first about the stability. Which one is the major contributor to the resonance here, A or B? Okay, so somebody said A and B. So B is a major contributor here. And the reason for that is because the negative charge is on oxygen, correct? So now let's go back to the second part of this question. So I'm going to draw the initial structure of the molecule here. And let's start talking about the hybridization. So what is the hybridization of this carbon here? sp2. Okay, double bond sp2. So this one must be sp2 too. So how about this guy here? sp3. And Devora. Okay, so this actually information answers your question. If you have an sp3 hybridized carbon, you cannot move negative charge or positive charge over there, because that will mean that you'll have to break the bond here. If you don't see it, you can draw yourself a Lewis structure of that with the hydrogens attached. And if you move the negative charge towards the sp3 hybridized carbon that I just marked, you will see that there will be 5 bonds towards this carbon, which is a wrong Lewis structure. Okay, so how about this guy here? What is the hybridization of this guy here? So sp2 or sp3. So when you look into it as a carbon anion, it looks like sp3. But if you look at the second resonance structure that we drew here, you see that there's a double bond now between these 2 carbons. So this is going to be assumed to be sp2 hybridized carbon. And of course, this guy here is sp2 because of the double bond, and oxygen sp2. Okay. So let's try now as another molecule. Let's say this is N molecule, okay? So again, we have the lone pair of electrons here. So now in this structure here, you can move your electrons either right or left, okay? So I'm going to move it right now first, okay? So you move electrons here, and then at the same time you move electrons towards the oxygen. That will allow you to draw the first resonance structure for this molecule, where you have a double bond here, and oxygen with the negative charge on it. Okay. So this is one of the resonance structures you can draw. You can also go the other way and use the second oxygen here to delocalize this charge. I'm going to draw the longer arrow here because that's different direction, okay? That will give you a molecule that looks like that. Okay, everybody can see it? Can you draw more resonance structures here? Yes, Gurneet?
Professor, can you hear me?
And I cannot hear you again.
Okay,
I'm sorry, can you type your question, please? Can you type your question, please? Oh yeah, sure. Like if there is more than one option, then you're welcome to do that. I mean, you actually will have to do that, yeah, or you will have to be able to recognize that. Okay, so the idea is that some of the questions that I will give you will be, let's say, oh, this is the structure, okay, and uh, how many resonance structure does this molecule have? What is the hybridization of each and every carbon here, for example, okay? Or how many sp2 hybridized carbons do you have in this molecule? Or this kind of stuff. So how do you know where to start? Well, you look at the structure and you see. So in this case, you have a negative charge here, yes? So the negative charge is where you have your lone pair of electrons. If it's a neutral molecule, then you look at the structure of the molecule and you find the most electronegative atom first. Once you find the most electronegative atom, you separate the charges over there and then move on from there if you can. Okay? Remember, the first structure that you have drawn that is given to you, it's also resonance structure. Okay, so for example, if I were to ask you how many resonance structures are possible for the molecule N, what will be the answer? 3, correct, because you have the initial structure plus 2 additional resonance structures. You have to keep it in mind. So how for the molecule K here, you will have only 2 resonance structures, but not 1. Okay, so sometimes students believe that the resonance structure is only the one they draw, and they do not include the initial structure. The initial structure is also resonance structure. Okay, so let's do the last example at the bottom here. Okay, so O example. So in the O example, now we have a lone pair of electrons at the bottom here on the carbon. Oh, I'm sorry. Let's go back here very quickly and then assign the hybridization. Okay. So what is the hybridization of this carbon here? sp3, correct. How about this carbon here? sp2, okay. About oxygen? sp2. How about this carbon here? sp2, correct. How about this guy here? sp2. So the oxygen will be sp2 again. So how about this guy here? This is sp3, correct. And also this and that carbon are also sp3s. So hopefully you can see it by now. And if you don't, please do practice that. Okay, it is crucial because that will be important for your test. Okay, so going back to the example O here. So in the first step here, what you can do, you can move the lone pair of electrons towards your pi bond. This is the only directions you can go because this carbon here is sp3 hybridized carbons. You cannot delocalize your electrons towards that. And at the same time, the double bond will move to this middle carbon. So by doing that, you created a first resonance structure that now looks just like that. Okay. In the next step, you can basically repeat the N example, which is you move electrons either towards the left oxygen, or you move them towards the right oxygen. So if you follow the right direction, you will get this molecule here. No, you cannot do that. I'm going to tell you just in a second. Okay, so let me draw the second structure here. So the second structure will look like this. Okay, so now the question is, how many resonance structures do you have for this molecule? 4 resonance structures. Okay. You cannot start from the oxygen because you already have a negative charge on your molecule. So this is the place that is the most electronegative for you. There is nothing more electronegative than electrons. So you cannot do that. Okay. You only separate charges in the molecules that are neutral at the beginning. Okay. So if there is any kind of positive charge present in a molecule, this is your starting point, either positive, negative charge, or radical. This is your starting point, no questions asked. Okay. The question is, how do you move those electrons around So neutral means that there is no charge in the molecule. So you see those molecules here have a negative charge. That makes them an anionic species. Okay, so these are anions, or specifically carbo anions. Okay. And they are carbo anions because they already have electrons on the carbon. They have unpaired electrons on the carbon. The lone pair of electrons on the carbon. So, which gives it a negative charge, yeah, basically. So if you look at the molecule here, just basically I'm giving you a molecule that already has a given formal charge. So because of that, you know that this is your starting point, okay? It depends on the charge, though. Either move electrons from the, in this case, negative part of the molecule, or you move electrons towards it if it's a carbocation, and I'm going to talk about the carbocations in a moment. You have to start where the charge is. That's correct. Depends, but it all depends. The way you start it depends on if it's a positive charge, negative charge, or the radical. So let's go back to this molecule here. Let's assign the hybridization. Okay, so this carbon here, sp. sp3, correct. Okay, so how about this guy here, and also this guy here, sp2, yeah. How about this guy here, sp2, and this one here, sp2, correct, and this guy here, sp3. Both oxygens are the same here, and I hope you remember that. sp2. This is the remaining carbon, sp2. Okay, so now we have a structure A, B, C, and D. Which one do you think is the major contributor to the resonance? C and D, correct, because both of them, so C and D are the major contributors here. So this is M and M here, because they both have a negative charge on the most electronegative atom in this molecule. Which one is the next one? You have a B, correct, B, because it has now 3 options to delocalize this negative charge. It's a tertiary carbo anion here. Also, because of the oxygens and because of the double bond here, it's actually like tertiary allylic. Okay, so the B will be the next one, and the next one will be, of course, A. Yeah. The rule is that no, that's not true. The rule is that you always have to evaluate all of your resonance structures, check which one of those structures obeys most of the rules, and the most important rule is that A, all of the atoms have an octet, and B, the negative charges on most electronegative atom. And then you can look at the number of the bonds and then the separation of the charges, okay? And of course, like if it's neutral molecule, this is like by default the most stable, the major contributor, okay? So let's look at this molecule here. So these molecules now, you see, they have a positive charge now. So in all of those molecules, we either have a positive charge on nitrogen or on the carbon here. Okay. So let's do first an example with the nitrogen on. If you look at this molecule, we have a nitrogen here that has a positive charge. That means it has to have 4 sigma bonds or 4 bonds to it. Okay. And then there is a double bond here that is connected right next to this nitrogen. So initially, you can move those electrons from the double bonds towards the nitrogen to regenerate its lone pair of electrons. By doing so, you made the nitrogen neutral, but the carbon that is below that positive. So that's the first resonance structure that we can draw for this molecule. Okay. Then you can take the pi electrons, move them towards the carbocation, and draw a second resonance structure. Okay, and then you have another double bond here. You can use that to move the electrons again towards the carbocation and get you another resonance structure. Okay, so now we have a structure A, B, C, and D. Which one is the major contributor here? Anybody else? So A is a major contributor here because all of the atoms have an octet. You remember I told you, octet is one of the most important rules here. Okay. So in the B, C, and D, you have this carbon here with the positive charge, and that means that there is no octet on that carbon. There is a lone p orbital that is unoccupied. So B, C, and D will not be minor contributors compared to the A molecule. So which one will be the next one? B, C, or D? What do you think? Okay, C, I agree, but also B. Because if you think about it, the probability for this positive charge to be delocalized between two different positions is more or less the same. Yes, so you can either get delocalized towards the nitrogen or towards the carbon here. And the same thing here happens with the molecule C. You can either use one of the double bonds here or the other one to delocalize your charge. And of course, then we have a B and C. Then the D will be the least stable here because it's a primary allelic. That B and C will be considered secondary allelic. The localized means that you can move electrons from one position to another by shifting the pi bonds in this case, yeah. So the localization basically is the ability for the charge to be distributed within the whole structure. The arrows just show you the directions of the localization, correct? And you have to use arrows, or you have to be able to read those arrows. Okay. So here we go. We have those. Four resonance structures now. We know that the A structure is our major contributor, and what is the hybridization of all atoms here in this molecule? sp2, correct. All are sp2. Of course, on your exam, I might not draw the structure A, but I may draw, let's say, structure D, okay, and ask you what is the hybridization of all of the atoms, and you still have to answer sp2, okay? Oh my God, Deborah, allelic means that you have a double bond that is connected by sigma bond to another carbon, okay? And this carbon, and this position here, it's called allelic. It can carry either positive charge or negative charge or a radical. And if it is positioned at that position, on this particular carbon here, then it's considered allelic. Okay. So let's do a T example here now. Okay. In the T example, all we have to do is just delocalize the positive charge that is on this primary carbocation. So you move electrons from the double bonds towards the carbocation, and you draw your first resonance structure that looks like that. Okay, at the same time, you can, of course, use another double bond here, move it towards the carbocation, and draw another resonance structure. Now the question is, can you draw more resonance structures for this molecule? Yes or no? Okay, so I agree with yes. The question is where? Where would you draw the additional resonance factor? Correct. You can use the lone pair of electrons from the oxygens and use that pathway to draw the resonance structure for this molecule. The positive charge now is on the oxygen. So now we have a molecule A, B, C, and D. Which one is the most stable or major contributor? Everybody agrees that it's D? So that's correct. This is our major contributor here. And it is a major contributor because all of the atoms have an octet, and it has the highest number of covalent bonds here. Okay, even though the positive charge is now located on the more electronegative atom, but the octet overcomes that. Okay, so so if D is this the major contributor, which one is the next one? And B, correct, because B is a tertiary carbocation. Okay, so how about what is the next one? C and A, I believe, yeah? That's correct. C and A are the same. They are equivalent, okay? So now if I were to ask you what is the hybridization of this carbon here, sp2. Okay, so the question is B is and C before B is before C. Okay, so the C is a primary allylic. C is a tertiary allylic. So the tertiary allylic carbocations are more stable than the primary allylic. Okay, and I think I said that in the previous part. Yeah, so just please make sure that we review the stability of the carbocations and carboanions and radicals. Okay, so in here, this is a sp2. So how about this guy here? sp2. This guy here? sp2. And this one here? sp2, correct. How about this guy here? Okay, it is sp2. Okay, if you don't remember that, you look at the previous one of the resonance structures, and there is a double bond there. So how about the oxygen here? Okay, everybody agrees that it is sp2. It is sp2 hybridized. Okay, because in the D structure here, there is a double bond between oxygen and the carbon. So again, this is the molecule where all the atoms are sp2 hybridized, except hydrogen, of course. Yeah. Okay, so let me stop sharing this and go back to that one. Okay. Okay. Can you see it? I will post some of the slides today, and tomorrow the practice exam. Okay. The practice problems, those practice problems that we are doing right now, I think they're already posted there. Let me check very quickly for you. Oh no, okay, I'm going to post them today, okay? Right now after the class, but they will be posted without the answers, okay? The answers you have to, you have to take your notes here, okay? So let's go back to the let's go back to the resonance structures. Okay, so here we have a carbocation here. This carbocation now, of course, can be delocalized, and so you can draw additional resonance structures here. So first, you would like to move the let's say this double bond, And by doing so, you will create a new carbocation. So we have a double bond now here, and then the carbocation now is on the terminal carbon. If you use the other double bond to delocalize the charge, you will move different way. And of course, this charge here then can be further delocalized by the double bond from the left here, and that will give you a third resonance structure. Okay. So now we have a structure A, B, C, and D. Which one of those structures is the major contributor to the resonance here? Okay, so not A and C together. If you're not sure about it, you have to look at those structures and think about it. Okay, so the A is a secondary allylic. B is a primary allylic. C is 1, 2, 3. I'm sorry, 1, 2, 3. So it's a tertiary allylic. I'm sorry, and it's also double allylic because it has two sets of conjugated double bonds here. Okay, so you can put double here. Okay, and the D is a secondary allylic. Okay, so if you do that, then or if you are able to recognize that, then it should be relatively simple for you to assign the priorities here. And the C is the most stable here. The next one will be A. A will be a little bit more stable. A will be a little bit more stable than D, because D has only one conjugated double bond, and it is secondary, but it's not double allylic carbocation like it is the A. Okay, so this is ×2 here too, because you see you have this double bond here and this double bond, so the positive charge can be delocalized both ways at the same time. Okay, and in the D situation, you have only one double bond here. So therefore, the carbocation can move only one direction. So the other stabilizing effect that you have here on this carbocation is called hyperconjugation and inductive effects. And so this is weaker than the resonance. So therefore, the next one is A, and right after that will be a D. And the last one is B. Okay. So let's talk hybridization now. Okay. What is this guy here? sp3, yes. So how about that guy here? sp2, correct. And this one here? sp2, correct. How about this one? sp3. This, and this. They are all sp3 hybridized. Okay, so how about this guy here? This is sp2, yeah? And all of the other ones, this, and these guys here are all sp2 hybridized, okay, because of the double bonds. Okay, so I see you picking up the. Okay, so let me draw it for you just as a cartoon here. Okay, so I'm going to draw it larger. Okay. Okay, so the first thing you do here is you look at the number of the substituents around your carbocation. It's 1, 2, 3. Okay, so that means this is a tertiary carbocation. Okay, and this part here indicates that this is allylic. It's one allylic group, and this here indicates it's also allylic. So there are two allylic groups. That's why it's a double allylic, okay? Tertiary double allylic. Okay? Maybe not this one. Oh, let's try this guy here. Okay, so if you want to draw the resonance structure for this molecule here, well, keep in mind nitrogen has the lone pair of electrons here. Where would you start first? With the nitrogen or with the double bond? So that's the question is, can you make a double bond here with the nitrogen? No, correct. The carbon over here is sp3 hybridized. You cannot use the nitrogen to delocalize charge here. So the only place you can move your positive charge is towards the double bond. So you take the double bond, you move it towards the carbocation, and you draw your first resonance structure that looks like that. The double bond is now here, and the positive charge is here. Okay. So now the question is, can you further delocalize this charge? How? Okay, so you're proposing something like that, yes? Correct? Do you think this is a proper Lewis structure? No. And I agree. This is not a proper Lewis structure. This resonance here will not occur because the positive charge now is on the oxygen that doesn't have an octet. If the oxygen has an octet and the positive charge, this is fine. If it doesn't have an octet and a positive charge, this is not the proper Lewis structure. Something that you have to remember, okay? I think this is the same situations where you have the separation of unlikely charges from the neutral molecules where you localize the positive charge on more electronegative atom. You cannot do that unless there is an octet on that particular atom. Okay. So in the previous example, that we did, where you had the this kind of scenario where the nitrogen had the positive charge, or another example where you have an oxygen with the positive charge like that. These two are okay because now oxygen and nitrogen has an octet, but the scenario that that I just crossed, it's not good because there is no octet on the oxygen. Okay, so that's something you have to keep in mind. So how about this? Oh, one more thing. Okay, so what is the hybridization here? I'm going to just point few positions here. Oh, I already said that. Yeah, so this is sp3. So how about here? sp3, correct. How about here? sp3, okay. And well, how about here? sp2. Okay, so you see, assigning hybridization is actually quite easy for you, I see. As far as they being contributors, okay, so what do you think? We have molecule A and B now. Which one is the higher contributor here, or the major contributor? A B, correct. This is the major contributor because this is a tertiary carbocation that is also allylic, and this guy here is a secondary carbocation allylic. Okay. So let's move to the next question here. Next problem. Now, nitrogen has a lone pair of electrons, oxygen has 2 lone pair of electrons here, okay? Okay, double bond between the carbon under the oxygen and the carbon to the right on the oxygen. So something like oxygen, double bond to carbon, and double bond to another carbon, something like that?
No, in like the previous example, I'm not sure if you can hear me now.
Jacob, is this the question? Where? Oh, you're talking about this situation here, where you separate the charge. Something like that? Because that's the only other possibility that you have here, and this is the invalid possibility. You cannot do that because you already have a separation of the charges in your molecule, so you are not supposed to add additional separation of charges. Okay? I hope this is the question, okay? So let's move on with that structure here. Double bond is moved to the left, like in this molecule. Like in this molecule here, but have a negative charge on the oxygen. Where would the electrons come from, and how would you change the positive charge to negative charge? You cannot do that. Since your molecule starts with the positive charge, it means every single resonance structure has to have a positive charge somewhere. Okay? Okay, so let's go back here. Okay, so here we have the resonance structures. Now we have a nitrogen that is right next to the carbocation, so it can actually indeed share electrons. So primary, secondary, tertiary, that accounts for the predicting the major contributor to the resonance. Okay, the four preferences. Yeah, these are the parts of it, but it's additional information that you have to keep in mind when you assign the priorities and you need. Okay. So the first resonance structure that we can draw here is the following. Okay, so by moving pi electrons from the electrons from the lone pair of electrons from the nitrogen toward the carbocations, you can make the ammonium salt here, and that's your first resonance structure. Another resonance structure can be drawn by moving electrons from the pi bond here, and you will get this molecule. Okay, so now the question is, can you draw more resonance structures here? No, you cannot. Well, Granit, you can call it a third preference, but this is like the fifth preference, yeah, if you want to. It's just the stability of each and every intermediate depends on its structure, yeah. And if it's a neutral molecule, well, that's your major contributor. But if you have a separation of the charges, or you have a carbocation or carboanion radical that you start with, those are governed by by their own sets of rules. Okay, that you need to remember. Okay. So no more, yeah. Here, so we have these three resonance structures here. Which one of those resonance structures is the major contributor? A, B, or C? Correct. C is the major contributor here. Which one will be the next one? A, correct, because it's a tertiary allylic carbocation, and then B. Okay, so what is the hybridization of this nitrogen here? It is sp2, correct. So how about this carbon here? sp2 again, good. How about this guy here? sp3, great. Very good. Okay, so you see, I think you're catching it up well. So hopefully you will be able to draw a nice molecules. Okay, so now let's look at this particular question. Okay, I'm gonna give you 2 minutes. Okay, yes, Deborah. Why is it tertiary allylic? Well, you have 1, 2. Oh my God. Oh, I'm sorry. There is an error here. I'm sorry. B is the second one, and A is the last one. The B is the tertiary allylic, okay? Because you have 3 substituents, and then in here there is a double bond, sigma bond, and a positive charge. That's allylic part. Tertiary, this is 1, 2, 3 different substituents connected to your carbocation. Okay, so please correct that the order here. The C is the first because of the octet everywhere, and the highest number of the covalent bonds. B because it's tertiary allylic, and A is the allylic. Okay, and and then we can move on to the next one. This one. Not this one. No, not this one. Where was this one? Not this one. This one here. Okay. So I want you to think for about maybe 2-3 minutes, and tell me how many it's not the secondary allylic. B is tertiary allylic. The A is the secondary allylic. Secondary still is less stable than tertiary. Okay. I want you to think about this molecule. Tell me how many resonance structures are possible for this molecule. Okay, I'll be right back with you. Okay, so what is the answer? How many resonance structures can you draw for this molecule? Okay, so we have 4. Okay, anybody else says? Anybody else have the other answer? Okay, we have also 3. Okay, so the number of possible resonance structures for this particular molecule is, I'm going to show you with the dots without drawing that, okay? 1, One has the negative charge here. One will have it on this carbon here, and one will have it on this carbon here. So that's total of 3, not 4. Okay? What is the hybridization of this carbon here? Okay. Are you sure it's sp2? It's sp3. Look, it's not connected to any double bond. It doesn't have a positive charge on it. So that means it must be sp3. There is no way you can use this carbon to delocalize the charge. That's why the terminal double bond that is on the right side here cannot be used to delocalize further charge, the negative charge that will transfer to this position here. Okay, and the if I were to ask you, is this molecule the major contributor to the resonance structure? What will be the answer? Yes or no? No. That's correct. The reason for the no here is that because, I mean, actually, yes. Or maybe no. No, because this is a primary allelic, but you can have a tertiary, but a double allelic. Okay, so resonance usually overcomes the just a primary, secondary, or hyperconjugation. Let's call it this way. Okay. When you think about the exam, okay, I may draw just one resonance structure and ask you how many other resonance structures are possible, and then just give you one, 2, 3, 4, whatever, yeah? Or just I can write down the sentence that says, analyze the possible resonance structures for the molecule above, and indicate that it possesses 1, 2, 3, 4, 7, 20 resonance structures, okay? The major contributor will be a primary, secondary, tertiary, or allelic or benzylic carbocation, or carboanion, or a radical. You will have to be able to use that vocabulary to answer the questions. Okay, I'm going to draw very quickly all the resonance structures for this molecule. So this will be the next one. And the next one will be this guy here. Okay, and the electrons will move from the carboanion towards the double bond, and from the double bond towards the carbon here, and then again here to get to another one. Okay, so as far as the exam goes, okay, let me see. Is A and B secondary, or A is primary, B is tertiary? Okay, so A, B, and C, correct? So A is primary, B is tertiary, but it's double allelic, and the is a secondary allelic. Okay. So let's go back to the questions about the exam. Okay, so on your exam, you may expect to see up to 15 questions. Okay, and the total number of the points available will be 100 points, and on your the types of the question that you will have to answer will be either multiple choice with one answer, multiple choice with the multiple answers, and for the multiple answer questions, you're always gonna have a partial credit, okay? Although for the multiple choice, multiple answers, you will get the negative points for answering the wrong question. So basically, wrong, for the checking the wrong answer. So you better check the correct answer that you are sure of than the check, like whatever you feel like, hoping that it will work out for you, okay? Because I will be subtracting the points for the wrong answers, for the multiple choice questions, multiple answers. Then there will be questions where they fill the blanks, okay? Usually fill multiple blanks. So you have to look at the question, look at the structure or the, maybe resonance structures or whatever the question will be asking for, and then use the proper vocabulary to answer the questions. So there will be a statement. During the statement will be either in the form of questions, or it will have these empty spots that you will have to fill up with the proper word. Usually a word, not a sentence, though. Okay, so it will have to be, let's say, let's say the carbon indicated by an arrow is a primary, secondary, tertiary, or allylic benzylic carbon. Okay, this is the second most stable, or the first, the most stable, or the major contributor to the resonance. I will give you some of the vocabulary in the parentheses, in the question. So you will be able to choose some of those, but not for all of the questions. For more like an obvious questions, you will have to just know them from the lecture. Okay. There might be one question, one maximum two questions where you will have to upload the answers. So that will be most likely molecular orbital theory question, and maybe one resonance question where you will have to basically upload your answer. For that, it's strongly recommended that you have your cell phone. That you have your cell phone already linked to your computer. So you take the picture, save it to your computer, and then there will be in this particular question there will be an icon that says upload the question. No, the questions will be randomized, and as well as the answers will be randomized. And also there is no backtracking, so you will have to answer your questions, and once you answer, it's done. And there is no way I can set it up in the way that there will be last two questions. Mohammed, I'm sorry. The practice exam will be posted tomorrow. Okay, so you will have one exam. In this exam, I will set one of the questions. With the option to upload the answer. So this way you'll be able to practice how to do that efficiently. Yes, you will have to upload your work before you move on. Yes, so that's why you want to have your cell phone, or if you have a scanner, that's even better. Just link to your computer, so you can efficiently and quickly do it. You will have plenty of time to do all of that if you're prepared for the exam. And the exam will be under, the practice exam will be under assignments. Okay, there will be a post for the final exam also, and normally under announcements you will see the link to the exam. So if you have a problem finding the exams under assignments, then just go back to announcements and click on the link. The exam starts sharp at 2 o'clock. Yes. So the Tuesday, the exam is on Tuesday, so there will be no tutoring on Tuesday, and not before the exam though. Okay, so I'm thinking about the help session for you on Monday, but I would like to do that in the morning maybe. So probably around 9 a.m. or so, I can do like 1 hour with you. If you have any questions, that came out to you over the weekend of studying, okay? And I don't think it's a good idea to have a tutoring session or any kind of help session on the day of the exam. By the time you should be just ready. Yes, so the practice exam will give you the correct answers, correct? Yeah. And Monday is fine. Yeah. That is fine, Ryan. Yeah. And so the practice exam will give you the answers. Yeah. So at least we'll check. We'll give you the correct answer to the questions. Perhaps not the reasoning, but the correct answer for sure. Yeah. So